Garden fresh, in fact. Today is the 29th of May, 2025, and you can catch the air. So you can catch the air. You can catch the air any way you want. Hey, you can catch the cave. On the air, on the line all the time, and on your smart device, so you haven't to listen anywhere, or listen at home on a Grace Tabletop Digital Radio. Teams is still not playing nice with me, so I do apologize for any technical glitches. But you know what? It's important that you donate to the station because no one else does. So if you can, please do donate. That is, any kind of currency is good, including crypto, gold, silver, diamonds. That's always nice. If you can't donate, that's cool because things are tough all over. So tell people about the station. That's just as good. And while you're at it, like, subscribe, comment on everything you find that we put together. Be it Shiny Side Out or Platos Cave. That helps us a lot. Because I'd really like to do this full time. One point in my life before I, leave this dark valley of ineptitude and general malaise behind. But yeah, so if you can, that would be really helpful. Excuse me. All right. Before we start broadcasting at you in anger, we would like to acknowledge the traditional custodians of the land from which we broadcast. And for Dave,
it is the Dark and Jung.
Thank you, sir. For myself, of course, the Dark people. Thank you. And with that, we'd like to pay respects to elders past, present, and future. Dave, I had to start the call, and then I had to add you as an extra person instead of just
extra. Am I a +1?
No. I mean, there's no option anymore. Like we just get someone in there.
Oh, no.
It's a longer kind of
yeah, it is
less elegant. But whenever you upgrade, you should expect that things are harder because that's normal.
Unless you've worked where I've worked in the past, and you end up with less product. Oh, it was too expensive. We couldn't get all those add-ons, but the business needs those things to operate. Oh, how much is that? And then it turns out it was more expensive. Their entire proposal was ludicrous, and we had to add them anyway on this new product, a different product, mind you, which is now more expensive because now we're doing exactly the same thing.
And that's what you want to hear, right?
Uh-huh. Yeah. It is the same person, though, at a factory where there is things being assembled beneath a very large, very, very large roof space. Machinery, millions of dollars worth of machinery, but very little wages spent on the people doing the assembly, and they wanted to delete those people, right? That's just, hey, that's the 21st century for you right there. However, wait, go on somewhere. Now, unless it's your particular forte or niche, the thing you like, the hobby that you think is amazing, it's very rare that a factory with factory workers whose let's just call a spade for a spade, whose hobby isn't golfing. The proposal was to I'm not kidding. The proposal was to put a little mini golf in. I don't mean like putt-putt mini golf. No, it's just a putting green in the recreational room. I don't think many people had seen a golf club in real life. The people, this salt of the earth people that I worked with in the factory. I was in IT though, just to be honest, and I fixed their problems. Those guys do a great job, and I have to put my hand out and support all of those people doing it tough and doing the hard work for everybody else. I need to watch them being designed out of jobs because of automation, but that's it's another thing. The golfing putting green that was proposed to be put into that was same person, and the only thing they did with it, which was really good, I gotta say this out loud. These little, it's about this big. It's a single finger thing kind of sticking up from the monitor that I had to configure automatically, but I did, which clips on the back of the monitor and shows someone who can't see you whether you're on a call or not, headset. So everyone's wearing headsets all the time with their double monitors. I had to fight tooth and nail to get double monitors because people were alt-tabbing between apps. But this little thing, like a lipstick thing that stuck up, was gold. Best thing that I've ever deployed anywhere, ever. Which showed the status. It used the hook from Skype to be able to show if you're on a call or not. It also worked with the Telstra cloud telephony product. Fantastic. I don't tell you.
Okay.
That was so good. But everyone complained, despite it being fantastic, because you start talking to someone and then they realize that you're talking at them and they go, oh, sorry, I'm not, they motion to you that they're on a call. You can't see they're on a call because the app's tucked in behind something else. So that was gold. It really did work a tremendous, a lot. And, apart from the redecorating, the color schemes, the mini golf, well, the putt golfing green, only for the CEO, by the way, and himself, because they're the only two that like golf or could afford golf. Apart from those little tiny little lipstick things, fantastic, best thing ever. Are they around now? Oh God, no. They served their time. You could no longer get the hook that made it light green or amber or red. Now we don't use, no, they don't, but we don't have a product. The Teams doesn't support it. So, Skype did. Skype was great. I like Skype. I feel like, Dr. Cox from Scrubs, when he has a huge rant about technology, and he says if they scrubbed all the porn off the internet, there'd only be one website left saying bring back the porn. And that was on a American television comedy medical show. So I feel as though I can say that on this channel.
If you can't say it here, you can't say it anywhere, my friend.
So that's true. You could say that about Blatton, Mecky. Blatton, the sweet little Swiss town.
It's no longer there.
What a wonderful... I had dreams of living in a little town like that. Sadly gone. It is soon to be washed away by a tremendous flood. I have a screenshot of kind of what it looks like now, and the scale of the horror is very difficult to fathom.
Oh, it's no longer there. It's just gone.
It's gone. It's just under gravel now. But the gravel has now filled up the bottom of the valley. But there was a river. There used to be a river. Those rivers, the beautiful Swiss Alps, should be a river going through the middle. It's now clogged. And it's somewhere between 40 and 60 meters deep of gravel. And what's going to happen, Mackie? What happens? The little river, the cute little river that people live right next to, it's going to fill up and flood over the top and eventually cut its new way through. But with 60 meters wall of water, when it does break this, it's going to be like freeing up a logjam. All the towns south of this on the rivers are going to be, hopefully, not touched, but inevitably endangered by the floodwaters.
Notwithstanding the claim of some people that there's no climate change, fair enough. I'm not going to get into the argument here, but I think we're going to see more and more of these events where things just fall apart. What I mean by that is in permafrost, in above the I guess the ice limit in mountains as well, where nothing grows and it's just permanently frozen in snow, snow-capped mountains and all that. As it gets warmer, I think we will see that a lot of these things were held together by the cold. Excuse me. So I think there's going to be, and I think we're seeing it already. There'll be more sinkholes. There'll be more landslides because nothing is holding it in place anymore. The frozen stuff is gone. It's just water now, and water, once it's liquid, everything just washes away and rushes off.
It's a lubricant, Mickey.
It's a lubricant.
It's a non-compressible lubricant.
Yeah, and not only that, it's one of the best solvents in the universe that we know.
That's right. That's because it has two different molecular structures.
Yeah, water is we actually have shown that water is a very strange thing. It's a very, very odd thing. But
it has 7 different states.
Yes, that is correct. And that's as far as we know anyway. And it seems to have memory as well, which is really interesting.
That's right.
But quite a few things seem to have memory. Honey has memory, which is fascinating. So there are certainly a lot of things that could go wrong as we enter this new era of change, where temperatures are now fluctuating in areas where they never really fluctuated. And I think we'll see structures falling. We will see, like I said, sinkholes, landslides, mudslides, rock slides, because it was probably just the frozen water that kept it all in place, right? And I think it'll become harder and harder for mountaineers to do what they love doing, mountain climbing. I think the Himalayas will get to the point where the lower sections will probably be off limits. I mean, the higher peaks should still be traversable, but again, you're taking your life in your own hands there. And you always have. I'm not saying that's new, but I think there is more of that going to happen. So, look, time will tell.
Well, time will tell. In this case, Becky, it was a terrible combination of failures. So the mountainside had formed a crack above a glacier and collapsed the, I don't know, is it 20 million tons of rock onto the glacier that's up in the Alps. And it then forced that glacier to come apart and collapse towards the valley floor. The glacier isn't there anymore, but it's likely that if the situation happens, it might be able to build itself back up again. So it's not a slip and slide, I suppose, of ice going down the hill. They had hoped that it maybe it would break up and come down in little bits, which would kind of be manageable. But looking at the outcome, there's not a chance that we're ever going to get through this.
No. And I think we've not forgotten, but we are less aware of these natural forces than we used to be, I think. Especially in cities.
Steady state, Mickey. Remember that? Gold.
That's not a thing. I'm sorry.
It's not at all.
It just isn't. So, I mean, it's okay. You can say that it is, but it isn't. Steady state is dead. It's as dead as the dodo. And it can't be brought back, with genetic engineering, cloning either. I think that we have to completely throw it out the window. In fact, I can't remember what it was, but I was watching so many things over the last few days, and so many things came up, and I thought about all of these different scenarios and the different approaches to science. And again, I looked in some detail at the quantum computing that's going on, where this quantum computer solved something in, I don't know, in 20 minutes or whatever it was.
It should have taken a billion years.
No, this is 25 zeros.
Oh.
25 zeros. Yeah, no, it was crazy. And then now everybody's talking about it as though it's a thing. Quantum computing seems to, I say seems to, others are saying it more definitively, seems to take place across the multiverse.
Yeah.
There's no other way, they say, to explain how it can do what it does as quickly as it does. Okay?
It's like it's connecting to the Akashic record. It just knows the answer.
but Akashic record across the multiverse,
All the multiverse, yeah.
which is interesting. Now,
I say that so casually. Oh yeah, that's.
well, it's these it's really fascinating because all these things that we sort of pushed aside, consciousness, the spiritual world, which goes anything really that goes beyond the material world. In the West, we have a real problem with that, right? Like we feel uncomfortable. And I get it, I understand that. But this is where we have to start looking now. We in anger, we have to look at all the connections that we thought severed, that we thought were no longer necessary. We are now calling things by a new name. UAPs instead of UFOs, quantum foam instead of ether. Because for the longest time, I learned in school that space is a vacuum. It's perfect. Nothing happens in space. No. I mean, there's some hydrogen atoms, sure, but they're few and far between. But for the most part, it's just a vacuum, nothing. Now it turns out, it seems that there is this seething, underlying quantum state, quantum foam, as it were, that seems to be everywhere and all pervading rather than nothing, which is exactly what the ether was, right? And if you don't like to call it ether, okay, that's fine, but you might as well, because that's what those scientists meant, right? And the funny thing is this as well: we only know about the localized phenomena, right? We're trying to determine the nature of the universe, the multiverse. Forget the multiverse, but the universe, by living in a tiny little corner somewhere on the outer fringes of some, galaxy, spiral-armed galaxy in a supercluster. And who's to say that the laws of physics are the same across the universe? I mean, speed of light. I mean, see, this is the funny thing, Dave. We have turned light into a solid. Scientists managed to turn light, and you go, what? How could you slow light down sufficiently to turn it into a solid? How does that make sense? Well, it doesn't, not really, but they did. They have. And you ask yourself, well, okay, then what does it mean for the speed of light? I mean, the speed of light is the speed limit. Well, let's be very specific here as to why it is. What Einstein said, and what his formula said: any kind of mass, anything with mass that is accelerated to the speed of light gets to the point, as it approaches the speed of light, gets to the point where its mass becomes infinite, according to the formula.
Exactly, okay? You got it right.
And that's the problem with light speed. Because mass, clearly could not be infinite, or at least, so we think. I got two questions, or two things I want to dive a little bit deeper into, Dave, and I want you to then also talk about your red and blue shift. So number one, what if you can eliminate mass? Just saying. Because something is traveling faster than the speed of light when you got quantum entanglement. And Tesla said he sent a radio signal around the world at a speed multiples the speed of light, right? But that's not possible. You can't do that, according to Einstein. So you've got the theoretical physicist, which was Einstein, and you had the practical inventor and physicist, the engineer that made things, that that actually said, no, you can't. There it is. And Fleddy is right. Well, tachyons, which might be particles traveling in time, through time, backwards in time, forwards in time. There's no time flow. It doesn't exist. It's something that we perceive, but in pure mathematics and physics, time flow is an illusion. It doesn't actually exist. So you have the speed of light as the speed limit, in my opinion, falsely. We know it's not true. Okay, and because let's say Tesla got it wrong. I don't think he did. Let's say he did. Fine, and we know it's still wrong because we have quantum entanglement, which communicates or transmits information instantaneously, which is a lot faster than the speed of light. There's another thing. If you go to a supermassive anything, like a black hole, right? The only solid object in the universe, a black hole. Remember what I said? It's the only solid object in the universe is a black hole.
Mm-hmm.
As light gets near the event horizon, it's so called because that's the last thing we see. It freezes. It can no longer escape. So light slows down to a speed of effectively 0. It also bends around supermassive objects. So light itself varies in speed, to be clear. Now, I have a question, and I've asked this question before, but I really would like to know the answer to this. Let's say you built a spaceship that is as big as the solar system. So it's a pretty big spaceship, right?
Mm-hmm.
But let's say we are type 5 civilization, we can do it. Right? We built a Dyson sphere, right? And now we built a spaceship that goes from, let's say the orbit of Mercury to the orbit of Neptune, for argument's sake. Yeah, that's how big it is. It's pretty big. And then we accelerate it to 0.99 the speed of light. Right? That's what we've done. Now we're flying at 0.99 the speed of light. And inside that spaceship, we built another spaceship, much smaller, at one end of the spaceship. And we accelerate that spaceship to near the speed of light. So now, bear with me for a second. When you're in a train, and the train accelerates, you can feel the acceleration. Okay? That's what happens. It overcomes your inertia, like your tendency not to want to move. Okay? And you feel it. But once the train travels, you don't feel the speed of the train. Because I've been on trains in Europe that travel at 250 kilometers an hour, and you could walk along the train. You didn't get thrown, or you didn't get thrown around the train, anything like that. You're now moving at the same speed as the train, obviously, right? So any speed that you go is 250 kilometers plus whatever speed you're going, right? Make sense so far? Because you're in the train. So your train goes 250, and let's say I'm running along the train at 10 kilometers an hour. Now I'm going at 260 kilometers an hour. Okay, for all intents and purposes. Because I got the 250 the train acceleration and then my 10 kilometers an hour as well on top of that. Okay, still within the same system. Now, if I put that into my long spaceship and I accelerate a much tinier spaceship inside that massive spaceship, so my starting speed is 0.99 the speed of light, for argument's sake. That's where I'm starting. That's where I am. Because I'm moving with the spaceship, and inside the spaceship, I'm in my spaceship, and the big spaceship is moving at 0.99. But I'm actually not moving at all. I'm stationary, right? I haven't started moving yet. But let's say I do, and I accelerate myself very, very quickly because I can. I've got a super duper engine. They've built it for me, and I can accelerate to 0.99 the speed of light. Okay? So yeah, it is calculus, Fleddy. That's exactly right. We're getting to limits and all that kind of calculation, right? But you're then traveling at 0.99 plus 0.99, the speed of light, no?
Mm-hmm.
That's correct, right?
That'd be
so if
1.98.
Yeah. But the point is, well, not really. It'd be more. But my point is, how close to the speed of light could you get within that scenario, right? And remember, mass would have to become near infinite. But if I'm already inside the spaceship and I'm at 0.99 speed of light, which is my resting speed, my resting speed relative to the rest of the universe, right? My resting speed is 0.99. Is my mass now near infinite, even though it's my resting speed? And what happens if I accelerate within, right? So I would really like to understand what it means. So Fleddy, they ask, what color is the spaceship? Red, of course, with speed holes. It's red because it goes faster. I think that's a no-brainer. So, okay, but let's forget that for a second. Okay? What if we could step outside of conventional space, like they do in Star Trek, right? Hyperspace, subspace, I don't care what you call it, and sort of a a dimensional cheat, a higher or lower dimensional cheat, where in a phased universe, or in a space between universes, or in a pocket universe, or whatever you want to call it, where the speed restrictions of light don't exist, right? And what about wormholes, right? When I punch through the fabric of space-time, right, and I'm traveling through the wormhole, I'm traveling at normal speed. I could even just step through it. But what I've done, I've brought the space together. So this is space, right? Flat space, and then you'll tell me the shortest distance from here to here is a straight line, and that's true. But not if I fold it. As you've seen this before, right? Now punch a hole through, and the shortest distance between point A and point B is 0, no distance at all. So there are all these ways to get around these speed limits, but I still think that Einstein may have gotten it wrong. Okay, and what if I could reduce the mass of whatever it is by slightly shifting it out of phase, which seems to happen with monatomic gold? We discussed this. So with ORME, I know I'm going all over the place here, but there's so much here that needs to be answered. No one is looking at it, at least not actively that I know of in the scientific community. And I do read some of the papers. No one is looking at all of this in conjunction. What happens if you do phase shift slightly out of it, and your mass is no longer there? What are you going to do then? Right? Then you should be able to accelerate as much as you like. In fact, we seem to be seeing that with the UAPs, or UFOs, we're observing today across the world. Right? Now, I'm not saying they're accelerating to the speed of light, but they're accelerating without any thought to mass or inertia. Okay? Because if you're inside that thing, you be catch up the way they accelerate. But that doesn't seem to matter. Now, either there's no one in there, or they have what Star Trek like to call, euphemistically, inertial dampeners. Inertial dampeners. So that technology seems to exist. But if that is true, if you could completely disregard mass, the speed of light is no longer your limitation. Make sense? That's what seems to be happening with the UAPs. Without any wormholes, okay, without quantum entanglement, what seems to be happening there, the mass of the object seems to be completely inconsequential. Right? Just wrap your mind around this for a second, and all of a sudden, light speed or multiples of light speed should no longer be an issue. They should no longer be. Yeah, burn me, burn the witch. It's called the theory of relativity, everybody. Okay, not the fact of relativity, the immutable law of relativity. You know what I mean? So what do you think, Dave? I want to throw it to you and bring in red and blue shift as well, if you may.
Oh, you got it. All right. So firstly, I'm going to start with the EM spectrum. Everything I've got it up on the screen, Becky. All of the non-ionizing radiation seems to be harmless to humans. All the ionizing radiation above the visible light is dangerous to humans. Just the way it is. You can see my mouse would be on the red shift, and then that's the blue shift because it's the blue end, but that ends up being ultraviolet and further. But it's only in this little tiny bit there in the EM spectrum. It's all the same energy, just the wavelength is smaller. That's it. That's all that is. Now I want to take it back to Meki's point here. The Google quantum chip sparks debate on multiverse theory. Yes, they don't understand how it was capable of solving the problem, a decades-old problem, very fast. In fact, too fast. And the only theory they can come up with is Google quantum chip Willow solved a computational problem in under 5 minutes, sparking debate about its implications for the multiverse theory. It's a tremendous thing. And I'm not talking about the people who have been underground too long. That's my joke about people working on government projects, or the Large Hadron Collider, for that matter, who believed that they were going back in time from the future to prevent its operation. And when you say who, themselves from the future, the engineers from the future that were them coming back in time to interrupt the production of it because they. That's a great, Fleddy. I love what you've put there. So that didn't happen, by the way. Just saying, it was just there were just errors. So, as far as the weight and speed that you were talking about, first I'll touch on this one. So, if you're in a spaceship, but it's so vast that you're inside a small spaceship inside it, and the whole thing was hollow, and you made the outside ship get to 0.99, the speed of light, and because it was so vast, and it would take minutes to get to the speed you wanted, and then be able to decelerate in your little spaceship inside the big one, and achieve again another 0.99 the speed of light, and then put the brakes on. That's great. I love the physics example here. You would effectively be going at 1.98 the speed of light, because the two things inside, you're inside the bigger ship, but it's doing that speed. It's like being on a train in your example, Mackie, where if you throw a ball to me inside the train when the train has reached a uniform speed, it's no longer accelerating or decelerating, it's just doing, let's call it 100 miles an hour for math, and that's 160 kilometers an hour. If Meki throws me a ball or I throw him a ball, or we toss it between each other at 30 kilometers an hour, for instance, that would be 190 miles an hour, one direction. And if I threw it back down the train from, I was further in front of the train than Meki, then that would take 30 kilometers an hour off the speed of the ball relative to an observer on the ground, and that means it would be doing 130 kilometers an hour, not the 100 miles an hour, 160 that the train was going. So it depends on which direction you were going, because effectively, if you're in that large spaceship, in the hollow one, in your small spaceship, but both as capable as each other, and you went the other direction, you could actually be stationary in space. But
theoretically,
once again, you're not stationary in space as space is. The space is moving. On the Earth, we're doing a crazy amount of speed. Our whole galaxy is turning at an even crazier amount of speed. So any speed that you did would have to then be calculated against stationary space, if that makes sense to anyone but me. I'm not a physics major, but I did physics. So the same argument can be made if you have a torch and you're inside your spaceship and you turn it on. Does it do anything at all? Some people argue that if you're facing it forward and the ship is, say, doing the speed of light, that no light should come out of your torch at all. Or if you're going a little bit faster, it should bend around and come and illuminate you, even though you're pointing it away from yourself. These are all ideas. They're all theories. So far, we can't do anywhere near these speeds, and to prove any of it at all, to be honest with you, the idea that E equals mc squared is the only equation, it's very simple, and I think it works for a lot of calculations, certainly for high school students and university students doing physics. But to have something that ended up having infinite mass doesn't seem to make a lick of sense, because it is relativity, but if you were falling into a black hole and getting faster, at one point you would be near the event horizon. However, you'd have sped up so much that your mass would then become infinite. And I don't believe that there's an infinite mass orbiting and not falling into a black hole, because that would be an infinite mass of all of the things that have ever fallen into it, because time stops for those, and that's why there's a perpetual disk around. That's how it's visualized anyway, at least. And I think there's a point at which that fails, the equation fails. It might work really well for sublight, and that's the end of it. Once Meki's example got to observing or the observance of UAPs, for instance, that's a very different thing. The talk is, the idea around that is that the craft itself has a field which detaches itself from this universe and all of the things that affect it. And so it's an isolated, like a, let's call it like a, you know, those little capsules that you can put sugar in, like making, you know, sugar tablets, or if you've got a little home pharmacy or whatever it is, I don't know what people do, whatever they do. I know you can buy those tablets. We have to do it for our daughter for some medications. We just get a bunch of powder. We have to make it up because you're not allowed to touch it with your fingers or have even finger oil on it. Otherwise, it changes the chemical composition of the medication and can be dangerous. So we have to do that with special stuff, right? So it encapsulates the crew and all the mechanisms within the UAP according to theory, and so that there is, you know, it can do 90-degree turns. It can suddenly appear in the distance. This is to the observer. I am under the understanding, and always have been, that it is anchored to where it is. Say you have two switches. You have an anchor to where you are, and the other one is you pull from in front of you some distant object, some place you want to be, and you pull that to you. And now you hold on tightly to that and let the other switch go, which anchors you. And suddenly you are now just at the other place. The observer sees you just dart across in impossible speed, but really you didn't do that. You didn't even move. You just pulled space to you, and then suddenly you're at that point. So this is all, I think relativity does a really good job of describing the observer effect on how things would operate once you get to this point. I believe maybe he knew. Maybe he knew, and all his math was trying to work out what that meant. The last point, I appreciate you, Mickey, so much, and our dear listeners who have put those really crazy things up in the chat room. You know that just equations, you know, thing that you see in memes. That's going on right now, and I have a theory. Now, you mentioned two theories. One was the transparent universe theory, which I actually did propose to my physics teacher, and then he sent me a link. You're not the first to have come up with it, but I never researched it. I had the idea of the thing, and yes, it is. It's like the other guy that made the wheel. The first wheel, no, yeah, you got all the accolades, but the second guy who didn't even know about the first guy's wheel, he makes the wheel and he gets nothing. The two people that made television at the same time. One guy makes it in black and white. The other one in England, he made it in colour. And people were too scared because it was too much of a likeness of somebody, despite having seen this in sci-fi for such a long time. Anyway, the other theory that I wanted to talk about was the theory that I have that the redshifting and Doppler effect that is apparently witnessable is not at all what it is. Not at all. And the reason
that's interesting.
Yes.
That's really interesting.
So this one is still about the same electromagnetic spectrum. We've done nothing to change this. It doesn't change physics. But I found a beautiful calculation of this. And I don't know if I'm the first person to come up with this idea, but in the conclusion, and the link will be in the chat. All the links are always in our videos. And this is: over extreme distances through space, the energy of light gradually diminishes or attenuates. We observe this phenomenon as a redshift, the tendency for the frequency of light to drop toward the redshift end of the spectrum. Redshift measurements indicate that the maximum distance light can travel as visible light may be 15 billion years, only as visible light, because it redshifts down into infrared and then down through, you know, microwaves, etc. And radio waves is the bottom. At this distance, 15 billion years, it will have attenuated into a frequency range that is below the visible spectrum, beyond this 15 billion years of light limit. There are countless billions of galaxies that are invisible to us. So I found someone who's now done all the calculations, which I can now converse with and put that paper together that I've always wanted to do, Meki, which was saying that with our eyes, with visible light, we can only see about 15 billion years. When we get past that, we're using microwave radiation. We can see further with microwave radiation. And it's also the reason why we came up with that 3K, 3 degrees Kelvin. When we look around in the universe, we keep seeing this temperature in infrared, which is 3 degrees Kelvin, seems to be everywhere. And everyone said, oh, that's the remnants of the Big Bang. Well, it doesn't turn out to be that at all. So that's where visible light's dropped off after we can't see it. And then once it gets past visible light's infrared light, and so on, until it is only in radio waves. That's why we have radio telescopes that can see or penetrate further and see the degradation of light. So the redshift is a presumption from listening to an ambulance coming towards you and then leaving you. You hear it pitch up as it comes towards you, it pitches down as it leaves you. And that was a presumption that was used to also calculate light. They said, well, if everything's redshifting, it's all moving away from us. So, and that, I think, is our biggest mistake. It isn't. It's just, attenuating or losing energy in its wavelength, becoming a longer wavelength, and that's why we can't see, and that's why these limitations exist, and that the universe is much greater than we can possibly even imagine.
And just to be clear, there have been many theories that were discarded in favor of the dominant theories of the day, be it relativity or Newton or whoever. It doesn't really matter. Theory of gravity, etc. Now let's just look at that just for 1 second. The theory of gravity. We have no idea what gravity is.
Still not really worked it out.
Yeah, I mean, I will say one thing. Okay, toroidal forces are playing a massive role in this particular universe, the way everything hangs together, because you can't think of space-time. Normally space-time is represented as though an object, a planet, makes a dent into a plane, some kind of
it's a way of
space
being able to describe it to our feeble minds,
which is completely incorrect. This is the most misleading illustration you will ever see in your life. It is not like that at all. You need to think of how, and this goes to what Dave said just a little earlier. You must think about how the planets, the suns, whatever, the galaxies are actually moving through space, right? And they're moving through space in a number of ways, depending how they're configured, right? Most objects are, if they get sufficiently big, are spheroid, I want to say, right? I mean, there are obviously examples where that's not true. Phobos and Deimos, for example, the moons of Mars. Other objects, asteroids, meteors, they're not spheroid at all, but the Earth is.
Phobos and Deimos aren't even large enough to have a collapse strength of those to make them a sphere.
Yeah, correct. They're not. There's such not enough mass. It just isn't massive enough. Now, but let's just look at the Earth. Just the Earth. Forget everything else. The Earth is a ball which is slightly squashed. Think of it like a slightly squashed ball.
An oblate spheroid.
And it rotates around itself every 24 hours. That's why we have got day and night, more or less. It also goes around the sun in roughly 365.34 days. Mm-hmm. So around itself and around the sun, right? But at the same time, the sun is also spinning around itself, okay? And moving through space while the Earth is moving around the sun. So the sun is moving, yeah? And the Earth is moving around the sun and the other planets in a similar fashion as well. And the galaxy in which the sun is, more or less, it looks as though, more or less stationary. Not really, but kind of, sort of. because we're always in the same kind of spiral arm, also moves around its galactic center and around the universe as well. So there's a lot of motion here, right? And there's probably more motion in galactic superclusters or whatever, right? So it is not an indentation in space-time that we see. It's a whirlpool. Think of it as a toroidal kind of motion. That's what it is, like a tornado, or when the water sucks out of your bathtub. That's the kind of motion everything is moving in. Everything is moving in that kind of motion. And that's why I think toroidal forces and toroidal energy and toroidal physics are at the very core of or should be at the very core of our understanding as to how the universe works, because it holds true not just in the big but in the tiny. We do know that there's an electron cloud, right, where within the atom particles are spinning around each other, right? Now obviously we don't see that, and it's completely unobservable to us in day-to-day life and all that. I get that. It gets even more complicated where things pop in and out of existence. They form like a cloud-like structure. But this toroidal motion is the fundamental motion in the universe. It is the most fundamental thing that we have, interestingly enough. And funnily enough, what does the Fibonacci sequence depict? It's a frozen toroidal motion is what it depicts. The Fibonacci sequence, which is evident in a nautilus shell, which is evident in the distribution of seeds on a sunflower, etc., is a frozen toroidal motion. That's what it is, right? And the Fibonacci sequence underlies most, if not all, natural phenomena, right? And for some reason we don't look at that. We're not looking at that, and we should. But we don't, and I don't know why. The closest we come is when we study, I guess, tornadoes and such, right, or hurricanes, where you have this toroidal motion, and we're trying to study the path of the wind and so forth, right? But again, I could be wrong, but toroidal physics was something that the Germans did a lot of, and if we can believe the stories, that's where the bell was developed, or it developed out of toroidal motion physics, as well as I think it's Anton Schauberger. If you haven't heard of him, have a look at Anton Schauberger and the way he studied.
I've seen his work. Yes, Schauberger.
Right.
Yes.
Yeah. So it's really fascinating that it seems to be completely shoved off to one side. Not even for no one is telling you can't study it, but no one is interested in it. Maybe deliberately so. I don't know. But it's definitely an area of physics we should spend a lot more time in, right? And if you look at any natural phenomenon, right, that motion I just mentioned, the toroidal motion, is fundamental to it. And it doesn't matter what it is. It's completely relevant because there's something that is moving like that, okay? Even us, our very atoms. I mean, we are on the spinning disk. I mean, we are part of the system, so we don't feel it. And that's why flat earthers say, "Oh, we should be spun off the Earth." Yeah, but when the train accelerates, you're not constantly pressed against the back of the train, are you? You're not traveling like this because you're part of the system.
But they won't go that fast.
I know, right? So the
stations aren't that far apart.
Oh, that's funny. Because once you become part of the system in motion, now of course, if the system happens to stop catastrophically, let's say the train hits like a brick wall or whatever, you will also decelerate. Same.
You won't decelerate immediately.
No.
You'll decelerate once you've collided with the thing.
That's exactly right. So the train is stopped by a wall. You are still traveling at the same speed.
That's right.
Okay? Until you too hit the wall. So if the train hits and you are here, right? You keep moving.
Yeah, totally.
Okay? Because as far as your body's concerned, I'm part of the moving system. Hey, I don't care if you're stopping, I'm moving.
Conservation of momentum, that is. So
exactly. So that's it.
I've got a thing, Mackie. It says, however, that is not all. The Earth orbits the Sun at roughly 107,000 kilometers per hour. Our solar system rotates around the Milky Way galaxy at about 700,000 kilometers per hour. Additionally, the galaxy travels at an immense speed away from every other galaxy. That's the bit I don't agree with. As the universe continues to expand, which I don't believe in, but at vastly differing relative speeds to each other. Our galaxy travels, it says, at 2.2 million kilometers per hour relative to the cosmic background radiation that permeates the universe. We've already spoken about that, but so I think just saying 2.2 million kilometers an hour, possibly plus 700, so that's 2.9 million kilometers, and we've got another 100,000, so that was basically 3 million kilometers per hour that we're traveling.
There's a lot of freaking flyer miles. Now, to be clear, I know, right?
In?
I don't know. In your next incarnation. But to be clear, what Dave has just proposed, let's call it the non-accelerating universe, for argument's sake. Let's call it that, right? Or the non expanding universe. Again, if that were true, dark energy and dark matter would no longer be required, because we only need dark energy and dark matter because we can't explain why we're flying apart. Gravity, right, should pull us together, but something is working against gravity in the accepted model. So we have to it's dark energy that's pushing us out. Okay, right, okay. And it's actually the dark matter, which also works against gravity. Okay. But we have not seen either. Yeah, we haven't seen either. We haven't seen it. It's like I want to cut my cake into 50 pieces, but I also want to eat my cake by myself. So, I'll just invent this imaginary place for cakes where I can have my cake and eat it. Dark matter and dark energy are the cake that you want to share and eat yourself all alone. And that's a really big problem.
Mickey. I've got a revelation.
Please.
That the 3 million kilometers per hour is faster than the speed of light.
Is it though?
Yeah, because the speed of light is 300,000 meters per second. And we're doing
kilometers.
833,000 meters per second.
Speed of light per hour. So it's 360,000 kilometers per hour, right?
So I just converted 3 million kilometers per hour into meters per second, and that turns out to be 833,000 meters per second, which is math faster. It's faster. 300 meters per second, or 299,000 meters per second is speed of light.
No, it's 299,000 meters per second.
Yeah, that's what I'm saying. And we're doing 833,000 meters per second.
See, at that point, it's interesting because physicists will say, well, you can't add them all up. Well, why not? Why can't I add them all up? They have the speed independent of each other. So if Earth is the closed system of the solar system, and the solar system is the closed system of the galaxy, why can't I add them up? It's the same example I gave for the spaceship, right? Why couldn't you add them up?
Mm-hmm.
Oh, because that's dark string theory.
Don't do string theory.
Pepsi, partial
credit. Only the Simpsons fans know what we're talking about. We've only got 1 minute left on the show.
So we've got 1 million.
Mm-hmm.
Yes, 1 million kilometers. Sorry, 1 billion kilometers per hour. That's the speed of light. 1 billion kilometers per hour.
Mm-hmm. And we're doing, we're doing 3 million kilometers per hour. Yes.
Yeah, that's so. I think light is faster.
Okay, it still wins.
Sorry,
That makes me happy. I didn't break the universe.
not yet.
Not today.
Yeah. So yeah, 1 billion or thereabouts kilometers. That's a lot of kilometers per hour.
Yeah.
If you think about it, because it's actually, it's 3,600 seconds, and there's the music in an hour. Yeah, we haven't broken the universe. All good. It's all good. I still will say though that look at this great stuff. Who's this from? This is Fleddy, right?
Yeah.
This is Fleddy. Thank you, Fleddy. That's exactly what I was talking about. That's exactly what I was. Hey, this was Platos Cave. Don't go anywhere. Let's go into the chat. Have a chat to Fleddy. He's just posted, or she, I don't know. Some really awesome stuff there. Don't go anywhere. Something else is going to come up. But most of all, Dave.
Be safe, everyone.